here is my plan. I will start with some history and some elementary observations just to warm you up. And then I will speak about some topological invariants. Dimension, homotopic groups, and homology groups, or homology vector spaces. After that, I will switch to some applied part of topology, mostly about persistent homology, and then I will return to fractal dimension. Okay, let's start with some history and some elementary examples. Okay, so this is the review talk. So I have to show you some persons, some like one of the main persons in topology. So of course, yeah, the main person is in topology is Henri Poincaré, whom I guess everybody knows due to his Poincaré lecture. Well, he actually created topology. Yeah, most important parts in topology that we know and that we study today. However, so these parts of topology, like homology and the concepts were developed by Henri Poincaré. But certainly he was based on some previous works, and in some sense, the first topologist was Leonhard Euler. About his formula for polytope, we will speak a little bit later, and also Felix Klein. So again, Felix Klein, I think you're familiar with the surname because of Klein-Bottle, but actually in mathematics, he's mostly known for his Erlangen program in geometry. So yeah, this is a kind of philosophical concept, how to relate geometry with symmetries. So in his time, there were some popular subjects like non-Euclidean geometries, and he proposed to study non-Euclidean geometries using their groups of symmetries. So like Lobachevsky plane and sphere and Euclidean plane all have different symmetries, and you can devise geometrical properties from the symmetries. And Felix Klein asked the question, so, okay, forget about geometry, consider continuous transformations of something. So we have some objects, we can continuously transform them. What kind of geometry corresponds to such group of transformations? This is a huge group. There are huge of symmetries, all continuous bijections or something. And actually, this is the basics of topology. So topology studies some properties of shapes which are invariant under continuous transformations. And actually, well, as I know, Felix Klein was the man who proposed the term topology to study these things. And in his time, topological ideas were called analysis situs, some analysis of forms or of positions. And yeah, two more persons related to my talk, Enrico Betti and Emmy Noether. So Betti is known for Betti numbers. So he invented this notion in one work. I guess that Betti is known for some other works, but in topology, we know him because we use essentially invariants called Betti numbers. And Emmy Noether, of course, is a famous female mathematician of 20th century, maybe the most famous. And she is known for many things. But among these things is the algebraization of the notion of homology. So she was the person who proposed to study, so these Betti numbers are actually numbers. And usually when we speak about numbers, numbers are numbers of some objects. Emmy Noether proposed the approach that these numbers should be treated as dimensions of some spaces. And this is very important and yeah, used everywhere. So this was a history. So now let's turn to some mathematics. Okay, so there are some basic sort of definitions. So this is hand-waving definitions, but it will be enough for us to understand this on this level. So for me, a topological space is some subset of RD, of some Euclidean space. Yeah, actually, this is a more abstract thing, but okay, let me understand by topological space just a subset of RD for some dimension D. And the most important thing in topology is the notion of like equivalent objects. So we call two topological spaces homeomorphic if there is a continuous deformation, like continuous transformation from one space to another space. Doesn't work quite well. Well, continuous deformation is just a bijection between x and y, which is continuous in both directions. So this is just a pair of continuous map from x to y and from y to x, which are bijective. Okay, this was supposed to be an animation, but it only works in Acrobat Reader, so I will skip it. But anyway, you will find the animated GIF on the internet, which turns a coffee cup to a donut. This kind of well-known thing that topologists do not distinguish coffee cup from donut, and there exists some animation. But okay, I will skip it because it's not so important right now. Okay, so we more or less understand what shapes are equivalent. So in order to establish equivalence, like homeomorphism of some shapes, we just need to write down a bijection, a continuous bijection between these two spaces. But maybe a more important thing for us is how to distinguish shapes. So, okay, some shapes are equivalent, some shapes are homeomorphic, but some are not. So when you look at these shapes, so these are surfaces, two-dimensional surfaces. Yeah, intuitively, of course, you can guess that they are different. Yeah? Like they are not homeomorphic. If you just move, well, suppose all these shapes are made of rubber and you can just deform them. You cannot get a torus from a sphere. Yeah, but how to prove it? So that's the basic question in topology. And okay, to prove something, we need to introduce some invariants. We need to introduce some characteristics which are the same for homeomorphic objects and which are the same for homeomorphic objects. And then we can compute this invariant for different objects and see if these invariants are different, then our shapes are different. That's very basic thing from some, yes, high school mathematics or something like that. And of course, we can invent some invariants from scratch. Like you can consider the number of connected components. So connectivity is some property which rubber object preserves when we deform them. So number of connected components is an invariant, and another invariant is dimension. So dimension is dimension is we all understand that like interval is not the same as the square because the interval has dimension 1 and the square has dimension 2. But actually, it is not so easy to define dimension. So yeah, we understand that interval has dimension 2 and square has interval has dimension 1 and square has dimension 2, but it is not so easy to define things that this dimension is invariant. I will explain it in a minute or so, not even 10 minutes. But anyway, all things that I wrote here do not distinguish these surfaces because they are all two-dimensional and they are all connected. So we need something else. And here is some notion that I will need in the following. So in the following, I will need the notion of cell complex. They are also called cellular complexes or CW complexes. This is all more or less the same. So we have a natural idea that to study some object in topology, we need to subdivide this object into simpler objects, simpler sub-objects. So actually, when I look at some surface, for example, it is a natural idea that I subdivide this surface into some pieces. And I require that all these pieces are, well, have very simple topology. They are essentially Euclidean spaces, or like disks, balls in Euclidean space. So when I look at such subdivision, I see like sub-objects of different dimensions. Like I have points. These are subsets homeomorphic to zero-dimensional Euclidean space. I have intervals like these edges. They are homeomorphic to one-dimensional Euclidean space. And I also have these spaces, which are essentially two-dimensional Euclidean spaces, well, up to homeomorphism. Well, anyway, I subdivided my topological space into some number of simpler pieces. This gives me some combinatorial structure and also the way to analyze a space. Of course, I can, for each space, I can take many subdivisions. I can take many cell structures on the same space. But anyway, on the picture, you can see some subdivisions for two-dimensional sphere and for two-dimensional torus. Okay, so let's take some subdivision and consider the following invariant. So I count the number of vertices, the number of edges, and the number of two-dimensional cells. I'm speaking about two-dimensional surfaces, so there are no more higher dimensional cells in this surface. I only have vertices, zero-dimensional cells, edges, one-dimensional cells, and faces, two-dimensional cells. Of course, each of these invariants, like number of vertices, number of edges, and number of faces, is not an invariant. I can subdivide a sphere into, well, as many pieces as I want. However, it is a good idea to consider the following number, which is called Euler Characteristic. The number is this alternating sum of these numbers: number of vertices minus number of edges plus number of two-dimensional faces, two-dimensional cells. And okay, here is the statement that I'm going to kind of prove here, that this number is a topological invariant. So it doesn't depend on the way you subdivide your surface. Okay, let's prove it. So it's kind of exercise that I used to tell to some high school students, and it is very clear. It should be very clear if you do not dwell into details. So we have like two subdivisions, cell subdivisions of the same sphere, like this red one and blue one. And I need to prove that this number is the same for these subdivisions. So the thing that I do first is write both these pictures on the same sphere. Like more formally, you take a homeomorphism from this sphere to this sphere, and it takes these edges and vertices on the same picture. So on the same picture, we have both this red network and blue network, and this tells us that for each two subdivisions of the same surface, there exists a common subdivision. So a subdivision, but by subdivision, I mean that I can take one cell structure and subdivide each cell somehow. So this guy is both the subdivision of this one, because you can look at this red one and it is subdivided by blue lines into smaller pieces, but also by the same reason, the picture here is the subdivision of this blue picture over there. So this proves that there exists a common subdivision, and this tells us that we only need to check that this number is invariant under subdivision. Yeah, okay, so we need to check that this number does not change under subdivision. And here is the standard way to prove it, and essentially this is the argument of Euler, so who invented like the formula for polytopes, but idea is the same. So I have a subdivision of some cell structure into a smaller structure. This means that each cell, like each two-dimensional cell in the bigger structure, is subdivided into smaller pieces. So I have this one black cell over here, which is subdivided somehow. And now I start to move to delete elements from this subdivision. So first of all, I delete this edge. I deleted it. When I delete this edge, then a number of edges reduces by 1, but also the number of faces in the subdivision reduces by 1, because two faces are merged into one. So we have -1 to edges, -1 to faces. The Euler characteristic does not change because it is alternate sum. Here I deleted this vertex. When I delete the vertex, then number of vertices is decreased by 1, and number of edges decreased by 1, because I merged two edges into one. And I continue in the same manner. So I continue to delete elements, and you can easily see that at which operation there are exactly two changes in the numbers of cells. So I delete things. Some cells are merged. So now I deleted a vertex and an edge, and again the number of vertices and number of edges changes by 1. So I continue this way, and I see that at each operation, Euler characteristic does not change. So essentially, I reduced my subdivided object into the original object and proved that Euler characteristic does not change. And this is a very common way to prove things elementary, that you look at some operations which allow to pass from one object to another object, and you just prove that under these elementary operations, some invariant is invariant. The most difficult part in these arguments is to prove that essentially two objects are related by a sequence of operations of some sort. All right, so we proved that homeomorphic objects have, homeomorphic surfaces have the same Euler characteristic, but now we can just calculate Euler characteristic for some particular subdivisions of a sphere and of a torus, and see that they have different Euler characteristics. This is why sphere is not the same as a torus. Okay, that's is not homeomorphic to a torus. Yeah, that's fine. But still, Euler characteristic, this is just a single number, so it is not a strong invariant. It is quite weak invariant, and we can see that actually you cannot distinguish between a torus and a Klein bottle using Euler characteristic, because both these surfaces have Euler characteristic 0. Well, somehow a torus and Klein bottle are very similar in some sense. So they are not homeomorphic, but well, it is indeed difficult to find some invariant which distinguishes them. But another bad thing about Euler characteristic is that, for example, for three-dimensional surfaces, like three-dimensional manifolds, it is completely useless, because it always equals 0. So again, this fact. So for three-dimensional shapes, you can also introduce subdivisions into cells and introduce this number of vertices minus number of edges plus number of 2 cells minus number of 3 cells. And this number happens to be 0 for all three-dimensional surfaces, for all three manifolds. Yeah, it's kind of a consequence of Poincare duality, but this can be proved again in some elementary terms. This is not very difficult.
Question.
Yeah.
And torus, is it a three-dimensional manifold?
No, the torus is two-dimensional manifold, but it lives in three-dimensional space.
Okay.
So it is important to distinguish between the ambient dimension of the space and its interior dimension of the figure. So torus is two-dimensional, but by torus I mean a surface of donut. So I do not take its interior.
Okay.
So there is a hollow inside.
Okay.
So it is two-dimensional because you can introduce two coordinates on torus, like how to say, longitude and latitude.
Okay.
You need two numbers to get position in torus.
And here you claim that for every closed three-dimensional manifold, yes? What do you mean by as well closed?
Yeah, closed without boundary.
Without
So,
boundary.
yeah, so some manifolds can have boundary, like if you just take disk or Möbius band, Möbius strip. So they have boundary. So for boundary, we don't have the statement for manifolds with boundary. But if the three manifolds don't have boundary,
and can you make an example provide an example of three-dimensional manifold, closed three-dimensional manifold?
Yeah, all three-dimensional manifolds, closed manifolds should live in spaces of higher dimensions, like in 4 dimensions. For example, you can take a three-dimensional sphere inside four-dimensional.
Now I understand.
Right. Yeah, that's a good question. So all three manifolds live, closed manifolds live in higher dimensions, actually. All right, so this was some introduction, and now I will tell something about fractals. All right, so yeah, maybe other questions about like this elementary stuff that I was talking about.
I have another question. Can you please return to the subdivision of, for example, okay, this spell is okay. No, a little bit later.
Later.
When we subdivide some sphere, yes.
Yeah.
How we guarantee that we will not make a hole in this subdivision?
Yeah, actually, there are no holes at all. So so this area here is white, but actually it is a part of our figure.
Yes, I understand.
Yeah.
But for example, theoretically, yes, we can place points on our sphere, and we can connect some vertices that we will make a donut from our sphere.
Because so now we prove that if we have two homeomorphic figures, they have but if they are homeomorphic, then you cannot like break them or make holes or something.
Okay.
So this maybe I can return a bit. Yeah. So over here, so you can do this not only with sphere. You can do this with a torus here and here. Anyway, this cell structure is essentially some picture on the surface on your surface. So these are two pictures on one copy of
surface. Should be on the surface. Yes.
Yeah. All these edges are. Okay. Yeah. It is. It is maybe. I draw them as straight lines, but they live on the surface. Okay. Yeah. Okay. Let's continue about fractals. So some very basic things about dimensions that I told you. That some curve has dimension 1, some flat figure has dimension 2, and like cube has dimension 3. So why do we have all these things? So here is one approach which kind of useful and used in many areas. Is the following observation. So you can ask how many walls of small radius do you need to cover each of these figures? So I take, for example, as a radius, I take 1 over n, some small radius. And how many walls of radius 1 over n needed to cover a curve? Well, you just cover one by one. So you go along your curve and cover it with walls. And you can guess that you need about linear number O of n walls walls to cover the curve. And to cover something, some flat figure, you need essentially some constant times n squared circles, yeah, both disks. And for three-dimensional figures, you need this number, n cube times some constant walls to cover a cube or something three-dimensional. And this is the basics, well, some approach to define fractal dimension. Actually, there are two main dimensions, Hausdorff dimension and Minkowski dimensions, which are very similar. I guess that this synthetic definition that I gave here is something between Minkowski and Hausdorff. But yeah, we do not dwell into details right here. Just remember that you need something like n to dimension, n to power dimension of the figure disks to cover a figure by, yeah, if the radius of the disk is 1 over n. So this is fractal dimension of the space of some space X. So we can define this this way. And why it is called, so why it is related to fractals? Because there is some interesting thing that you can devise figures whose dimension is, dimension defined by this formula. This dimension can be a fractional. Yeah, here are some examples. So, for example, you can consider this Sierpinski triangle. So you take a triangle and cut a hole. Yeah, kind of. You take a solid triangle. You take a solid triangle and cut a hole. Yeah, maybe. So this is a solid triangle, and here you cut a hole, and then you cut holes over there, and you continue to infinity to cut holes like this. Then you get Sierpinski triangle. So this is one of the basic examples of fractals, and you can estimate the number of walls that you need to cover this guy. So essentially, when your walls become smaller, then you only need to cover these small pieces. There are not so many of them. So this Sierpinski triangle is, well, something between a curve and a flat figure. So it is more too fat to be a curve. So it is something more than one-dimensional, but it is less than two-dimensional. So it is there are too many holes to be two-dimensional. So, and essentially you can just compute this fractal dimension and see that this is a logarithm of 3 with base 2. Something like that. And there is another example with Menger's function. So Menger's function is again some hollow things like that, and you can compute its fractal dimension. And here is an exercise that you can, it is not very difficult, at least to understand why this is true. That if you have a self-similar figure like two figures over there, then you can compute their fractal dimension very easily. So, for example, this triangle is composed from 3 smaller triangles which are similar to the original one, with homothetic coefficient 1 over half, and 3 means that you have logarithm 3 here, and 2 means that you have logarithm 2 here, and this is the statement. But anyway. Why it is important. So, maybe about 10 years ago, when I was PhD student and I was preparing to some PhD exams, which contained questions about fractal dimensions, I found that fractals are used somewhere. So I entered PubMed, and this 10 years ago, when I typed fractal at PubMed, there were about 6,000 results. Now, so yeah, yesterday when I prepared my slides, there were 12,000 results of like medical papers containing fractals. And well, I guess that this high bar over there means that there are a lot of papers about fractals and Kadit. I guess so. Well, I don't have other explanation for this very big bar in the previous year. Yeah, but anyway, why fractals are related to medicine?
It might be due to COVID because many people started to write a lot of papers. There is this bar, if you look in PubMed, also for other types of publications. It's quite interesting.
Yeah, thank you. Yeah, maybe so. Yeah, but in particular about people write about fractals. Yeah, but anyway, why fractals? Because like cortex is something like a fractal, lungs are something like a fractal. So they are complicated and different zoom levels. Like so, I don't know. So you can compute some invariants like fractal dimension to estimate, well, to get some numerical characteristics of cortex or lungs or something. So that's one thing. Yeah, but unfortunately, there is a bitter truth that fractal dimension is not a topological invariant. So I started from some homeomorphism and all stuff in topology, but fractal dimension is not an invariant. And here you can see a very simple example why it is not. So on the left side we have a Koch snowflake. Again, one more famous fractal. And on the right side, you have just circle. And they are homeomorphic because essentially Koch curve, Koch snowflake is a closed curve. So it is just a curve. So it is the same as circle from topological point of view, but they have different dimensions. So you can compute dimension of Koch snowflake from the exercise that I told you previously, and of course dimension of the circle is 1. And another example, which I guess can be interesting to people who work in mathematical physics. This is more like recent modern object called Brownian map. This is a kind of two-dimensional analog of Brownian motion, and mathematicians started to do this stuff maybe 15 years ago or something, and there were wonderful results. So okay, let me show the picture. So this is a kind stuff like this is called a random map, but essentially this random Brownian map is a probabilistic topological space. So this is some distribution on topological spaces, even on metric spaces, and it was proved, more or less recently, that this probabilistic space has, it is homeomorphic to two-dimensional sphere with probability 1. That's one funny thing. And another thing that with probability 1, it has fractal dimension 4. So most of these contributions about these subjects are made by Legal, one of his authors, I guess that's in some French mathematician. All right, so here we have some examples. Okay, now for some time we are going to forget about fractals and turn to classical algebraic topology. We will return to fractals at some moment, but for now let's go to topology. So, are there any questions about fractals? About the previous part? Yeah, okay. If there are no questions, let's go further. And now I will speak about some very standard topological invariants of spaces. So dimension is not an invariant. Now I will speak about invariants. And essentially, the invariants that I'm going to define in the following are invariants not only of homeomorphism, but of another equivalence relation, which is even more common in topology. So okay, let me first draw some pictures over there. So I have, for example, this annulus on a plane. So I take a disk and pick a hole inside this disk. This is one space, and this circle and this is another space. And they are not homeomorphic. So, okay, let me write this down, that they are not homeomorphic. And it is easy to see that they are not homeomorphic because when you cut any 2 points from a circle, it becomes disconnected. So if you cut it into places, throw away 2 points, then this becomes disconnected. However, if you pick away 2 points over there, any 2 points, it cannot become disconnected. So they are not the same from some basic definition. However, they are going to be homotopy equivalent. So next, I will speak about homotopy equivalence. So homotopy equivalence essentially means that there is the same structure of like holes inside 2 objects. So this object has 1 hole inside of it, and this object also has 1 hole inside of it. And we can kind of collapse this this space into this space by like picking points from like these intervals, just to single points for each interval. And after this collapse, we get this circle. And this is what I'm going to define more or less formally. So this is the notion of homotopy equivalence. So first of all, when we define this homotopy equivalence, we need to define homotopy continuous maps from one space into other space. So now suppose that we have 2 spaces, x and y, and we can map one space into another space. Okay, another picture. So for example, yeah, this is one space, and this is going to be y. And another space, for example, circle, x is mapped to this y. So we have some map from a circle to this space, which is essentially a closed curve in this example. And we can consider different maps. Like, for example, the first map places this circle inside this space like that, and another map, so this is the first one, and another one is, for example, this one, and third one is something like that. So we can map x to y differently, but we say that 2 maps are equivalent if one can be deformed to another. So for example, here I can deform first map to the second map, just move this image of a circle inside y, so that this first image matches with second image. I can move it continuously to do this. But this first map is not equivalent to third map, because in order to get this image, informally speaking, I have to somehow move this line across this hole, and it is forbidden. So I only live in the space y. I don't have these points over there. So 1 is equivalent to, in this example, 1 is equivalent to 2, but 1 is not equivalent to 3. So this is a notion of equivalence of maps. And using this notion, there is the second definition is a bit artificial. It is not very easy to understand what is written here. However, I wrote it down that two spaces are homotopy equivalent if there are there are two maps x, y are equivalent if we have two maps that if you go this way and this way, you will get the map from x to x, which can be deformed to identical map. And if you go along these two arrows, this composed map is identical to, is homotopy equivalent to identity on y. That seems a bit strange at first time, but this is a very nice definition, which you can prove many things from this definition. So here is again some pictures that I wrote here. So in these pictures, so this is the first, essentially this example. So how you can show that these two spaces are equivalent? You need to define two maps from one space, so map from here to there and from here to there, and they are written here. So for the first map, I just need a map which collapses, as I told you, the map that collapses each interval to a single point. And the backward map is just the inclusion map of this circle inside this object. And you can prove that this condition is satisfied, that when you go this way, this is identical. This is homotopy equivalent to identity, and this way the same. And another thing is this example. So this pink space is homotopy equivalent to this 8 figure and also to this figure, and they are all not homeomorphic to each other. So even these two graphs are not homeomorphic, but anyway, they are homotopy equivalent. So this is an example of homotopy equivalence. And the basic invariant, which is studied in topology, is are the so-called homotopy groups. So homotopy groups are the groups that show how you can map spheres or high dimensional spheres into your space. N's homotopy group is the set of equivalence classes of maps from n-dimensional sphere to X. Okay, let's understand the basic thing. Maybe I will skip some details over here, but just to understand the definition. So suppose we have n equal to 0. So this tells us that we need to map a zero-dimensional sphere into our space X. Zero-dimensional sphere is just a couple of points. So zero-dimensional sphere is the boundary of one-dimensional ball. So these are just 2 points. And suppose you have some space X. In this definition, we need to fix some base point in this space. So, point X naught. And we also fix some point of this zero-dimensional sphere. So now you need to map these 2 points into this space so that base point here maps to base point here. So essentially this map goes like that, and this point can be mapped to anywhere, right? But now I consider everything up to homotopy equivalence. So I allow to move the point, to move the image. And you can move the image of the second point. So for example, this is the first map, and this is the second map. You can move the image of the second point inside each connected component of X. So, and if I send this point to different connected components, then I cannot move from one to another. So this is essentially the explanation that pi naught of x with base point x naught, that this guy is just the set of connected components. And you can go further. You can map a circle, like on this picture. And again, the ways how you can map a circle into your space then gives you this first phi 1. This is also called the fundamental group of the space. And it is something more complicated. So this phi 1 of x consists of all the ways how you can map circle into this space up to homotopy equivalence. So for example, here I have this way, this loop, and this loop, and maybe some loop like that, and they are all not homotopy equivalent. So this fundamental group counts loops inside your space.
Excuse me, could you repeat please, what is x0?
Just any point inside x. So this is just additional information. I pick some point inside x. You can choose it differently, but well, in most cases it is not so important which point you choose. But you just pin where one point on the sphere maps inside x. That's the requirement in the definition. Yeah, for some reason it is important. Well, for example, if I do not pin the image of one point, then even pi naught, this group, will be bigger than the set of connected components. You need to choose images for both points. So so I just forbid. So I require that this point maps to some fixed point in x. Yeah, this is just a part of the definition. And something that I'm not going to explain is that for n equal 1, 2, etc., these are indeed groups. So there is an operation of combination, like composition of maps of these loops. So these are groups, and starting from 2, these are abelian groups. They are commutative groups. Yeah, but anyway, this is an example of homotopy equivalence. If x is equivalent to y, then they have the same homotopy groups. Yeah, I do not now. I do not write these base points over there because they are not so important for us. And essentially, these homotopy groups are, well, in some sense, the strongest possible invariant of topological space of homotopy equivalence of topological spaces. Because here is some famous Whitehead theorem, which tells that, well, essentially tells that if two spaces have the same homotopy groups, then they are homotopy equivalent. So it is the statement that I said is not correct, but the statement written there is correct. So if you map one space to another space and see that this map gives you isomorphisms of all invariants, then it is a homotopy equivalence. These are good news, but here come bad news. So actually, you cannot do anything with homotopy groups. They are very complicated for several reasons. So first of all, this fundamental group pi 1 is non-commutative, and non-commutative groups, non-abelian groups, are very complicated from algorithmical point of view. So actually, you cannot distinguish you cannot recognize groups if they are not commutative. That's another famous theorem of Adian. And for higher n's, these groups are commutative, so they are abelian, but they may be infinitely generated. So they also may be very awful. So they are not computable. And yeah.
What do you mean write the program compute for, it is impossible to find it on Turing machine or something like this.
Yeah, and this too, and this too. But even so, you can read here that you cannot even compute this invariance even for spheres. So spheres are the most like simple topological objects, but even for spheres they are not computed in any sense. There are no algorithms. They are essentially we do not know it. Well, we know something about these groups, but it is always some work by hand, very complicated mathematical work. So, for example. And another thing about these groups that they are not intuitive. So, for example, you can map three-dimensional sphere to two-dimensional sphere in infinitely many non-homotopic ways. So, it is impossible to understand. So, okay, you can consider some construction, but that's very strange thing. That you can push three-dimensional sphere into two-dimensional sphere in infinitely many ways. That's awful. And here is, and here is some scary table about homotopy groups of spheres. So as I told you, there is a problem to compute homotopy groups of spheres, but for some small values of maps from Sn to Sn, so they are classified. And here is some. Now, even for small values, there is a complete mess. So, there is a very messy table over there. And if you learn topology, you can understand zeros over here, and that's over here, and probably if you are very good, you can understand this Z2 over here. But all other things, well, I don't understand all other things. That's too difficult for me. So even for spheres, you cannot compute them, and of course you cannot use these groups to analyze some data or something because, well, they're very bad. Okay, so let's forget about these homotopy groups as this is a nightmare. We cannot do anything with them. So instead of homotopy groups, we now turn to.
Yeah, what does mean uncompatible? You can distinguish
You cannot prove the isomorphism of two groups if they are given representations with generators and relations. So, for example, if you have two such representations, you cannot tell you cannot recognize a trivial group. So if you have some generators and relations, then you cannot algorithmically it is impossible to tell if this group is trivial or not. That's again against results. So instead of this awful homotopy groups, we turn to their like simplified version. Simplified version is what is called homology. So here, let's speak about homology. Okay, let's start with graphs. Okay, we all like graphs. So here is a graph on this picture. Okay, this is not an edge. So these are edges. Okay, how do you think? What do you think? How many cycles does this graph have? How many cycles are in this graph?
6.
Yeah, 6. So you can compute like this cycle and this cycle and this cycle, and also this cycle, and there are other cycles. But notice that essentially there are 3 cycles, and like you can pick, for example, this cycle and this cycle and this cycle, and you can get any other cycle which you can imagine as a combination, as like sum of these basic cycles. For example, okay, let me show you on this picture. So so I mean that I only need theta 1, theta 2, and theta 3 to generate all other cycles. For example, this theta 4, this cycle, is like a sum of this cycle and this cycle. It is kind of Boolean sum. When you take this cycle plus this cycle, then this edge contracts because it is contained in both cycles, well, in some sense. So you only need 3 cycles to describe all cycles as linear combinations. And this is kind of like the basis for definition of homology of cycles. So we can consider, by cycle we mean, so okay, let's forget about the cycle in graph theory. Let's say that, well, for example, a cycle is a collection of edges such that at each vertex we have even number of edges, of adjacent edges. So this is true for all these pictures. And if you give this definition, then you can notice that you can add, you can take Boolean sum of cycles, so that these all cycles form some vector space over field with two coefficients, or over Booleans. So essentially, the cycles are not separate objects, but they have structure. They have the structure of a vector space, well, over F2, over field with two elements. And by the number of cycles, I mean the dimension of this vector space. So in this case, this dimension is 3, because we only need 3 basic elements, these 3 elements, to generate everything. So these are the basis of the vector space of cycles. But there are other bases. So for example, I can take this one, and this one. They are also bases of this vector space. But anyway, the vector space has dimension, and dimension equals 3 in this example. So this 3 actually tells you that your graph has 3 holes inside. Like this hole, and this hole. So there is a way to count number of holes in a graph using this vector space of cycles. And in graph theory or in algorithms complexity theory, this invariant is called cyclomatic complexity of a graph. So if you are interested, you can look at Wikipedia what it talks about.
Excuse me, is the purple picture is also a cycle?
Yeah, I also call it a cycle. Yeah, right.
Despite it's disconnected.
Yeah, right. For it is like algebraical cycle. Because I want to have freedom to add cycles. So when I add cycles, I get a cycle. And then if I add θ1 plus θ3, I will get this purple one. So for me, this one is cycle. This is not a cycle in graph theory, but in topology, this is a cycle.
And empty cycle.
And empty cycle is also a cycle.
So 2 in power 3.
Yeah, 2 in power 3. Yeah, I haven't draw this empty cycle, but essentially, we have vector space of dimension 3 over field of 2 elements, so it has cardinality 8. There is 0 somewhere. And here are some definitions. I will briefly go through them. So to get things formal, you need to consider. So now we consider not only graphs but any cell complexes. So in a cell complex, we have vertices, edges, and, for example, 2-dimensional cells. And in this cell complex, I can define the vector space of 1-dimensional chains. These are just all combinations of edges with some numbers. So a chain is essentially So for example, we have this 2-dimensional complex. It has some edges. And I put some numbers on each edge arbitrarily. 5, -1, 3, 4, etc. And all such combinations are called chains. They form a vector space because you can add them and multiply them. And inside this space, you can define, or somehow define, a subspace of 1-dimensional cycles. And inside this space, you can define another subspace called the space of boundaries. So boundaries are all boundaries of 2-dimensional cells. Like when you look at this triangular cell, you can take these edges with coefficients 1, 1, 1, and all other coefficients are 0. So this is a cycle. But this is a very particular cycle. It is the boundary. It is the boundary of something. So we have this collection of subspaces. So we have a subspace of boundaries inside the space of cycles. And then you can take the quotient space, cycles modulo boundary. And this is called the first homology. Let me show the picture. So you have this two-dimensional complex. It has vertices, edges, etc. And you have cycles. So you can forget about two-dimensional cells in this picture and just look at the graph over there. So we have graph. In the graph, we have cycles. But we now want to say that some cycles are the same. So they are equivalent. We say that this green cycle is equivalent to blue cycle. Why? Because if we subtract, from this one, we will get this combination of two cycles, but these are not just like arbitrary cycles. They are boundaries of cells. And this is why we say that this green cycle is the same as homologous to the blue cycle. So this is a kind of algebraical or combinatorial version of things that I did here. So I can move like curves inside my space continuously, but I can define it algebraically like this homology equivalence. So I say that some cycles are equivalent to each other by introducing this notion. And then these cycles modulo boundary are called homology. Yeah.
Can you repeat this idea of homology?
Yeah. So here is the definition. So we have vector spaces, all vector spaces of all cycles, vector subspace of all boundaries, and you need to take the quotient vector space, cycles modulo boundary. So this is a formal definition.
By this slash, you mean you need to subtract one set from another set?
This is not subtraction. This is the quotient vector space. The quotient vector space is the space where you artificially define these vectors as zero vectors. Like you map all this guy to zero. Boundaries. Yeah. So the thing is that boundaries should be zero in my homology.
But if we define the operation of modulo operation, yes, we should define what is the modulo operation.
It is vector space. This is the vector space.
Vector space.
Yeah, it is a vector space. Yeah. It is still a vector space, and well, essentially what we need to know is that dimension of this vector space is the difference dimension of this space minus dimension of this space. This is all we need to know.
Okay,
Можно тоже узнать? Вот я не понимаю. Если мы возьмем следующий, если мы возьмем внутренний цикл и внешний цикл, они же тоже должны быть одинаковыми.
Yeah, interior. Yeah, they are also homologous.
А почему, если у них взять разность, они же как бы не получится?
It will be the sum of all boundaries.
Да, хорошо.
Yeah, essentially there is a question of signs over there. So essentially you need to put some orientation on each cell, and in terms of orientations, the boundaries that you define are not just the sum of edges, but sum of edges with plus minus signs. So essentially there is some difficulty with sign over there, which I'm not going to strictly define. But anyway, the idea is that you can do all these things in all dimensions. So you can consider collections of not just edges, but of two-dimensional cells, three-dimensional cells, etc. And you can do almost the same things. So you can define cycles, boundaries, and homology ends homology. Okay, here is the definition that you can define cycles, boundaries, and you can define degree n homology as the quotient. So this is the difference of vector spaces. These are called n-dimensional homology. And this is essentially the definition of homology, but computationally we need its dimension. So its dimension is called nth Betti number of the space X. So what is so this all this stuff has some clear geometrical meaning. So beta naught of X, so dimension of zeros homology vector space, just counts the number of connected components of X. And again, you can prove it using some definitions which I skipped for now. But I guess that my presentation will be available, so you can see what's going on and restore some details. But anyway, this beta naught again counts number of connected components of X, while beta n in general counts the number of n-dimensional holes in our space. So, for example, maybe in example here, one-dimensional homology will be, degree 1 homology will be a one-dimensional vector space. So essentially, this is a vector space generated by a cycle which goes around this hole. So homology counts holes in our spaces. And in this particular space, one-dimensional or degree 1 homology is one-dimensional. So beta 1 equals 1 because it has one hole. And these beta n's in general count some higher dimensional holes, whatever it means.
Yeah. One more question. And in the previous slide, you talked about first homology. You mean that it is one-dimensional homology?
I mean that it has index 1. So we have H0, H1, H2, H3, all they have some dimensions. Dimensions maybe not one.
I don't know. I mean, in the previous slide, first homology it is only the number.
This is a vector space, and its dimension is the number beta 1. Yeah. Okay. Okay. I have quite a little time, so okay, but let's discuss what is good and bad about homology. So essentially they are good because to compute this homology we need to deal with finite dimensional vector spaces, and this reduces to some operations with matrices, essentially Gaussian elimination. So they are algorithmically computable. All these beta n's, Betty numbers, are computable. And here, if dimension of your space X is D, then it doesn't have any topological features, any Betty numbers in degrees greater than D. This is also good to know. So for example, if I draw pictures on a plane, then I cannot get beta 3 or beta 4 or etc. for these pictures because they are all two-dimensional. And they have some geometrical meaning, and they are invariants. So again, this is non-trivial. However, if X and Y are homotopic equivalent, they have the same Betty numbers. And well, another thing, and this thing you can prove that the alternating sum of Betty numbers is the same as alternating sum of number of cells. Vertices minus edges plus two faces, etc. This was in the beginning. So essentially, this is the way to prove that this characteristic, this Euler characteristic, is an invariant in general in all dimensions. So they are related to this very simple thing from the beginning of my lecture. And bad things is that they are quite weak. So these invariants, Betty numbers, are weak. They are sensitive to noise, whatever it means, because they are integral. These are integral numbers. And it is difficult to compute them. So essentially, Gaussian elimination is an operation which takes a lot of time for big data. All right. So now I will briefly go through applied topology, essentially through persistent homology. So there is a lot of stuff in applied topology, so many things. Persistent homology is only one thing that I will tell something today about. So what is persistent homology? This persistent homology is some device to analyze dynamics on topological space. So instead of only one space, I consider a collection of spaces, and each next space is bigger than the previous. So I have a collection of spaces indexed by real numbers. So xt is a collection of spaces, and whenever s is greater than t, then xt is a subspace of xs. I will show you some pictures. Yeah, okay, so here is a picture. I have this timeline. And during this time, my space changes somehow. So in this picture, I have these 3 points at time moments from 0 to 4. At time moment 4, some two edges appear. Then some other edges appear, and some new cells appear in this filtration, in this sequence of spaces. So this is essentially the picture of filtration. But if we have this sequence, then you can look what happens with topological invariance in this sequence. So, for example, now we have not just one space, but like infinitely many spaces. And for all these spaces, we can compute, well, for example, compute its Betti number. This is kind of some integral number associated with the space. So instead of one number, you get integral function. Well, something like that. So you have this time, how your space changes. And at each time moment, you can compute Betti numbers. So Betti naught, Betti 1, etc. And you have pictures like that. But, well, notice that this is reasonable because our space can change only in finite number of time moments. So essentially, most of the time, the space remains the same. Usually, so formally, it is a requirement, but in most situations, this holds. And moreover, you can not only consider this graphic of Betti numbers, you can also consider what happens with different topological characteristics through time. So, for example, we have this 0-degree homology, which counts connected components. And we can look what happens with our connected components. So, of course, through all the time, we have some component, one connected component, which lives infinitely. So this is one component. But some other components die when we add some edges. So when we connect 1 with 2, then some component at this moment dies. And we also connected 2 with 3, this also dies. And at the same moment, some new component appeared, this 4. So we have this storyline of another connected component, and this component dies at this time moment because we connected it to something else. And at the same moment, some cycle appeared here. So we have this one-dimensional hole over here, and it appeared, and it lived. So this is the element of first-degree homology group. And this cycle lived until this moment when we glue it with some triangle. And there are other cycles which appear at this moment and this moment, and they again died some time. So we have pictures like that. And this is the idea of persistent homology. So persistent homology is like a storyline of topological features through time. So your time changes, topological space changes, but some topological features somehow, at some moment, they are born, and at some moment they die. And essentially, this collection of intervals is what is called persistent homology. Okay, let me show you maybe. Yeah, so this is what is written here. So when I have this filtration of topological spaces, I can define these storylines of homological features. So essentially, in each degree n, we have a collection of intervals indicating that the corresponding topological feature is born at time moment bi and dies at time moment di. So essentially, this is a kind of data which we attach to a filtration. And they are algorithmically computable. Yeah, maybe I will show some code over there. So again, there is a different representation of the same data. So just for each of these intervals, I draw a point on a plane with coordinates time of birth, time of death. So I can draw pictures like that. They are called barcodes. So this is barcode representation of our persistent homology. But of course, I can just encode each bar here by two numbers on a plane. This is what essentially is done here. And this is called persistent diagram of homological features. But what is the profit of all these things? Essentially, we want to consider only those topological features which live long lives. So we can compute the lifetime of each topological feature. This is the moment of death minus moment of birth. This is how long this feature lived. And we say that topological features which live longer lives are more important statistically than topological features with small lifetimes. Okay, so and on this diagram you can estimate the lifespan by how far the point is from this bisector, from y equals to x line. So this point, so this represents this feature is kind of more important than this feature, which is represented by this point. So, well, essentially, persistent homology is a way to introduce some statistic to topology. Basically, topology is not friendly with statistics because topology works with some discrete invariants. However, now we have some points on the plane. You can compare them somehow, and you can make some decisions. You can compare real numbers, and this gives you more information about what is going on. And yeah.
Can I ask you, what is the meaning of the node homology?
Okay.
Node zero homology.
H naught connected components. So H naught counts connected components. So now we have 3 components. So they live until we connected them. So these components live here, but 2 of them die because we connect them to each other. So at this moment we connect some components into one, so they merge, and then some other component appears, etc., etc. So H naught counts connected components. This is important. Okay. So now, so let me briefly sketch what to which data can we apply persistent homology. We can apply persistent homology to point clouds inside Euclidean space. So for example, we have some finite set of points in RD. And well, our problem can be formulated as follows. Suppose that these points are sampled from some surface, from some manifold inside RD. What can we say about this manifold? How we can restore this manifold from these points? Or can we understand topology of M from this manifold? And this can be done. Using so-called Čech filtration. So this Čech filtration is the union of balls around these points, and the radius of these balls increases with time. Maybe at this moment I can show you some demonstration. yeah, I hope it's works. So okay, here we have some point cloud inside three-dimensional space, and each point I can surround each point by a ball, and well, you can see that basically these points are sampled from something like a circle. So there is some circle over here. Yeah, good. And we want to recover this circle. What do? We surround each ball each point by a ball, and take union of these balls. And at some moment, the union of these balls becomes resembles this circle from which points are sampled. So essentially, we want to consider this filtration, this increasing filtration of balls at all time moments. Of course, for some small time moments, all these balls are disconnected and it is not very interesting. However, when we proceed, somehow a cycle appears over there, and this cycle is given by this blue line here. So this is a one-dimensional homology which lives for some time. And we proceed as follows, and of course at some moment everything merges into a big cluster, and it is not very interesting to deal with this object because it doesn't have any topology at all. So everything, this cluster has trivial topology. It has only one connected component, and this is a guy which lives forever over here. Okay, so this is a very basic demonstration, and you can play with these particular examples by the link. So now let me return to the presentation and maybe say a few more words at the end.
No, another one.
All
one.
right. So we have this persistent homology, and we can actually. So okay, I will keep this. And we can actually use it to analyze graphs. Yeah, maybe I shall say a few words here. So essentially, you can do this this trick with expanding balls if your points are not points in some Euclidean space, but just some abstract vertices with some distances between them. So if you can just take some metric graph, you can take a collection of points and choose some distances between them, and then you can do essentially the same thing that I did with these balls, increasing balls. You can consider some filtration, which is similar to this union of balls. This is called Viettori-Sips filtration. So you can do similar things for all metric graphs. And now it is interesting to see what happens when you take some graph at random. So I take a graph on n vertices, and I choose distances between each vertex as a uniformly distributed value from 0 to 1. So I take distance uniformly from 0 to 1. And then I can compute persistent homology of the corresponding Viettori-Sips filtration and see and try to analyze it. And my point here is that we do not know what are the general properties of this thing, but we can do some experiments. Okay, I wanted to show them, but I'm a bit out of time. So I just say you that if you generate this random graph and compute its persistent zero homology. So zero homology is essentially a stuff which counts connected components. And now I just take the sum of lifetimes of all the zero-dimensional homology. And I made several experiments and and got some constant, always get some number around 1.2, independently on the number of vertices. So the sum of lifetimes of all zero-degree homology is about 1.2. Okay, so maybe somebody know what is the constant 1.2? Do you know some constants like 1.2?
1.
Yeah, good constant, but this is not. Yeah, it is about 1.19, 1.23, something like that. It is around 1.2. Yeah, okay, I can show you some funny things. This is called a Curie constant, and this is the value of zeta function at 3. Yeah, that's not easy, but this follows from some theorems. Yeah, okay, you can make some experiments with homology to compute the value of zeta function. That's kind of funny. But anyway, you can also do some experiments not with random graphs, but with random point clouds. So essentially, you can generate some point cloud from some distribution and consider its persistent homology. And take, for example, sum of lifetimes of some homology. And again, you can do some experiments, and at some moment you will see that you can estimate the dimension of the point cloud, the interior dimension of a point cloud from persistent homology, from zeros persistent homology. This is a kind of known theorem, probabilistic. However, it tells you that you can find the dimension, some sort of fractal dimension, based on homological features, based on homological characteristics. So here's some formula which also contains some logarithms over there, which is very fractal-like. And well, essentially that's almost the end of my talk. That essentially you can define some sort of dimensions which are called persistent homology dimensions, PHI dimension, out of persistent homology data, and it resembles some complexity characteristic of your space or of your data set or something like that. But essentially about this invariant, nothing is known mathematically, nothing is proved. So we have those theorems which I mentioned over there, and there are some experiments. So this is a kind of exercise for everybody, that you can do these experiments by your own and try to invent your own characteristics which combine persistent homology and fractal dimensions. And with big probability, you will be the first person who invents them, because not too much is known in this field. So please think about that. And that's all.